you all for coming, and I really want to thank the organizers for all the work that they put in for the last 2 years to bring this to this moment and giving me this honor of opening the conference. So I want to talk about attention to. I want to draw your attention to quantum complexity, and I don't know whether that was a title that I have given, but in this talk, I want to kind of survey different efforts that my group have been putting in to explore various aspects of quantum complexity. So what do I mean by quantum complexity? So well, let's think about what is not complex. That's a good way to start. So you have, let's imagine you have many fault-tolerant qubits, however many you have. This is a very simple state if every qubit is just pointing downwards, like it's a product state. If you have such a simple state, no matter how large your Hilbert space is, you are exploring only one state, just this one state out of all this exponentially many possibility. So this is very not complex. So what is a complex state? A complex state would explore the full breadth of your Hilbert space, and it is something that you can achieve perhaps by entangling many of the qubits. So I think of complexity of quantum states as like Janus has 2 faces, the Roman god. There is a face to which one face of this quantum complexity is that because of this space that your state can cover, by preparing one state, you will be able to access all of it in principle. So that's sort of the potential for being able to address classically hard problems. There is a sense to which this is a resource. But there is another face to this Janus, which is that it is very challenging to read out. So I want to talk about each of these faces and how we try to make generate value, intellectual value, value for humanity out of complex quantum states. So first, sort of forward-looking, positive-looking side of what complexity means, that it will allow you to attack classically hard problems. Now, well, what is a problem? So we have what we have in mind as a problem here is not, how to solve the world peace, but it is something that you define as solvable through means of programming. Programmable hardware, programmable systems is one of the themes of this conference. So you are interested in solving something through programming a hardware to execute an algorithm. So this is an example of a very first program written. This is program written by Ada Lovelace. And what she came up with, which brought perhaps us to today's computing, is when Babbage said, I have this machine which can do stuff. She had the idea to endowing this machine with memory where you can hold your previous step and being able to execute a sequence of operations. So the problem that she had in mind for demonstrating the power of this computer, perhaps the very first classical computer, was to calculate a specific kind of polynomial called Bernoulli numbers. So Bernoulli numbers are something that it's something that you can define algorithmically. So I want to emphasize this notion of algorithmic definition. So you can define a sequence of steps that you have to follow. Just it becomes hard to do it by hand because number of possibilities grow. And if you can see this screen, you see that this very first computer was literally using just 4 arithmetic operations. But what she figured out is how to make those operations, the iterative operations, happen through programming, a sequence of actions. So now in that line, how do we want to find a classically hard problem that you can bring value through quantum computer? Something that I want to share is a work that I've done with my collaborators and colleagues at IBM. And we were looking at a particular problem where its problem definition is you can give an algorithmic solution sort of strategy for solving a problem. Therefore, there is a sense to which you can give a classical instruction. But that classical instruction-based approach quickly run into the wall because there is a combinatorial explosion in possibilities. And the problem that I want to talk about is this idea of estimating or calculating chromatic polynomial. And this was work that just recently showed up in Nature Communications with a group of wonderful collaborators. So what is a chromatic polynomial? Chromatic polynomial is something that you define for a graph for an argument. And so for illustration, I'm going to use a simple graph. Here is a graph. Graph is defined in terms of nodes and the links, the edges. So here's a very simple graph. To calculate a chromatic polynomial for this graph, I'm going to ask, what are the number of proper coloring given the number of colors k? So these are just two possibilities. I can color this graph with red and blue. If my k is 2, there are just these two possibilities. That's simple. If I have 3 colors, already I have many more possibilities. You don't have to use all the color. Just that's the palette that you work with, and the rule is it has to be a proper coloring. Now, even for this simple graph, the number of possibilities quickly grow as you increase the number of colors. And here I have illustrated this for the original definition of a chromatic polynomial with the argument that is an integer, but mathematicians have expanded this to all rational numbers. So if I'm given an arbitrarily large graph, calculating chromatic polynomial is a sharp-p hard problem. That is, when you give a coloring, it's easy to validate whether it is a proper coloring or not, but counting up all possibilities is hard. But there is an algorithm. The algorithm is there is a simple recursion relation. There's this recursion relation called deletion-contraction relationship. It's a problem in the sense that I've defined. It is a classical problem, but it is a classically hard problem. So how do you approach this alternatively? The proposal we made in this paper was to prepare a state called Fibonacci string net condensate. Now, Fibonacci string net condensate does not allow you to evaluate chromatic polynomial for arbitrary argument. It allows you to evaluate for one particular argument. That particular argument is the golden ratio. But it is a problem that has been defined, and it is a challenging problem. So how do you approach this? Not through a classical recursive approach, but through a preparation of quantum state. So there is a quantum state called Fibonacci string net condensate, which is a superposition of many different configurations. And for each of these configurations, what I would do is to make a dual graph, and measuring the amplitude of this configuration would amount to evaluating the chromatic polynomial for this particular dual graph. So it's been known that the concept of Fibonacci string net condensate was something that's known as a topologically ordered many-body state, but how to prepare it on hardware that is available today was, there were various ideas, but none have been actually implemented, and that's what we did in this paper. So the way we approached this was the earlier ideas, when Levin and Wen came up with the idea of string net condensate way back, the mission, the goal was, the intellectual drive was to think about a topologically ordered state as sort of a solid state system. If you want to think about a solid state system, you might want to think about lattice, and you want to think about thermodynamic limit. So this string net condensate was originally prescribed as a ground state of a projector Hamiltonian, which has many spin interaction terms. It's kind of scary. 12 spin interaction. You know, who wants to engineer 12 spin interaction? We approached this from a very different perspective. Our approach was that we want to prepare this state And we want to do it in a way that we can grow the state as the hardware capabilities grow. So we approach this as, let's see what is the minimal ingredient. And the idea was that although if you think about this as a Hamiltonian problem, there's a 12-spin interaction, but the construction of a Fibonacci string net condensate as a many-body state is a very local constraint. There are local constraints that allows you to think about this as a local object. So we thought of what is the smallest string net condensate we can make, and we realized that, oh, well, you can just put one qubit under S-gate rotation, and it's nominally a legal state. And then you can grow that out as a string. It's kind of a bead, and you can fold it, and then you can stitch it back together, and you can build out string net condensate as your system becomes available. So this was our idea. We called it dynamical string net preparation, DSNP, which is to say we prepare locally and then connect them together and then build it out. And this, following this approach, we were able to prepare the state on IBM hardware. And it's easy to draw on a piece of paper. To implement it on a hardware is always a lot more work than you might think from your doodles on the paper. Many people would know this. Here is, I think Zlatko prepared this to show, if I want to show the full depth, it's just too wide, it doesn't fit. But it's still going. It's a very deep circuit, but we're tough and we've been able to do it. So what have I achieved doing this? So these are experimental results. So we prepared string net condensate. So concretely what we've done is prepare the string net condensate with 4 plaquettes. So these are 4 plaquettes. And if I prepare that state properly, I would have superposition of all these different subgraph configurations. But it is not a superposition of equal weight. It is a superposition of very specific weight. So when I measure that weight, I'm measuring the chromatic polynomial associated with dual graph of that subgraph. So for just 4 plaquettes, you can do that deletion completion algorithm classically and know what is it that you have to get. So here I am showing the comparison between the experimental result and the theoretical result, classical prediction. First thing to notice is I talked about a complex state and how the challenge of complex state is that you got to somehow cover it all to see that you have it. With the string net condensate, although the state is complex, there are a lot of possible bit strings that are not allowed by the rules of the state. So in we are still seeing weights because the experiment was done on a hardware that is still noisy. But if in the future, if you had a fault-tolerant computer where you can prepare this, and you prepare the state, these are not going to occur, which restricts the space that you have to cover, that you will see as a subset. And by measuring the amplitudes, you'll be able to estimate the chromatic polynomial. Moreover, there is multiplicity in the subgraphs. So this graph has 14 other representations, which is topologically related to this graph. So the graphs that have multiplicity tend to show higher accuracy. Something that we are exploring right now is to try to get a meaningful estimate of at what size will be given the cost of measurement, where, if any, we will have an actual quantum advantage compared to the classical algorithms running on a classical computer. But I want to highlight this work as sort of an example and sort of a direction and strategy for finding value out of quantum hardware by thinking about classically hard problems. Now I want to switch gear and talk about the other phase, the harder, the challenge outlook side of it. So what's the challenge of working with complex states? And if you actually want to work with experimental system and learn something from it. By definition of complex states, there is large sample complexity, and with our limited access to a quantum system, given the rules of quantum mechanics, figuring out what you have is a very hard inverse problem. So in tackling this side of the complexity phase, we have been trying to leverage AI. So that's what I call AI for quantum. So in trying to learn what is it that you have prepared in dealing with the complex quantum state from a data-centric perspective, instead of comparing to classical simulation, which you don't want to be doing, at least not forever, is to leverage AI. So this is something that we've been doing for a couple of years, and it's gaining more traction, and more people are joining this kind of direction. And I wanted to share, I mean, I can go into various projects and show like paper after paper, but I thought maybe it would be more meaningful to share, some wisdom, insight that I've gained doing this for a couple of years. And it is very nicely summarized to this theorem. So there is actually a theorem called no free lunch theorem, and you can find the result here in 1997. And it in computer science, and it means what it sounds, meaning that there is no magic bullet, and no algorithm can be good at everything. So if we want to do something that is practically impactful, being able to gain value out of your finite, hard-earned set of data, then it is really important that we don't go with the expectation of magic bullet and free lunch. Instead, you have to find an approach that is really precisely linking your data side of the problem, what kind of state that you have, with the meaningful strategy for the algorithm, centered around the data structure. What is the structure of your data? And what is your learning goal? When you want to teach or when you want to learn, you have to know what is it that you want to learn. And same here, you need to know what your learning goal is. So the first work that I want to introduce is something, this work just came out on Science Advances. This was work in collaboration with a large group of people. My longtime collaborator in the CS department at Cornell, Killian and his group, and experimentalist colleagues, and my students and postdocs. And especially, I want to acknowledge Yuri Lenski, who was a postdoc at Cornell when we started this, who came to me, and said, there's this problem called the problem of quantum complexity, and it will be really hard, but it will be really cool if you can do that with AI. And I didn't know anything about this problem. I learned it all from Yuri. Yuri didn't know anything about AI, and it was an adventure. But through this adventure, we built a strategy we call quantum attention network, which is really designed as that kind of a click between the data problem, the structure of the data that you face when you're working with snapshot type of measurements, and the kind of thing that you want to learn. And this is the rough kind of caricature of the architecture. But important thing was, we're banging our heads against this problem for several months. There was a specific problem of wanting to learn the depth of the random circuit just from the data. It was not working, and we were going through brainstorming and trying to figure out why is it not working. And as we were going through what the architecture is doing, Yuri said, look, the data you have here, the data we have is not like language. We're using language model inspired algorithm, the attention mechanism, and the order shouldn't matter. And Killian, my collaborator, said, oh, so you mean this is not a sequence, but you should be treating it as a set, that we have to be respecting permutation invariance. This is the example of that click, figuring out what is the structure of your data, what are the constraints, what's the symmetry in your data, is critical for coming up with an effective strategy. Once we figured out what is it that we needed to really get right, as something that we pass on to the AI algorithm and structure the algorithm around, we were able to really make things work. So what are the cases that we were able to solve? We were able to learn the relative complexity between two states in these three different problems. First is to distinguish the area law state from the volume law state for the hardcore boson data, and then to compare the topologically ordered state versus trivial state. That is, this is the side of Tori code with error rate that is under the threshold. This is over the threshold. Just from the data, we were able to learn the error threshold. And we were able to distinguish the data from random circuit that is from the deep circuit versus the shallow circuit. So the key approach that allowed us to do this was to use the self-attention, attention mechanism, which learns the correlation between two entries that when you enter, and then look at a nonlinear aspect of it. This is the mechanism that powers the language model, which allows you to pick up the important correlation between words in your sentence. And we used each of the snapshots, bit string measurements, within the set as to treat the entire set as a token. And this approach was successful in learning these, distinguishing these three different type of problems. More recently, we extended this approach to studying the measurement-induced phase transition and this measurement-induced dynamics, together with Roman and Roman student. And this was something that you can find a preprint in here. The basic idea here was that we were looking at translationally invariant hybrid dynamics with weak measurements, and we wanted to see whether we can come up with the protocol and the machine learning strategy to learn MIPT without post-selection and without accompanied classical simulation, just from the data. So what is it that we have to learn? So here our measurement is set up to be using an ancilla that is entangled to the system that's been scrambled to a varying degree. So these are the measurements. When the entanglement is very weak, when we look at the ancilla is going to be just a random binomial distribution. But when the entanglement is large, the ancilla is going to suck out information from my scramble state and reflect what is the state of this scramble state. This is a beta binomial distribution as opposed to Porter-Thomas distribution because we are thinking about finite sample size. So the actual task here is we looked at two kinds of tasks. One is, can we distinguish two different, both scrambled initial states? And another task, which is easier, is to see, can we tell the same scramble state that is undergone a weak measurement versus strong measurement? This latter is a simpler task. The first task of can you really distinguish the data from one scramble state from another scramble state is a very difficult task, and this is often referred to as learning the learnability transition. Here is what the measurements look like. This is what the bit string measurements look like. And this, looking at the actual data, getting your hands in this bucket of data help you appreciate what is it that your model will have to learn. So here, what is shown is the measurement trajectory at an early time. So at a very early time, when you have weak measurement, this is just the ancilla measurement outcome. So ancilla really doesn't know anything about anything deep that's going on in the scramble state. It's been initialized to be up sigma z, and that's all you see. So there is nothing you're getting out of it. But in the strong monitoring phase, in the strong monitoring limit, having started from one initial state of psi 0 and started from the other initial state of phi 0, then you can tell that both of these are very complex state in the sense that the weight is distributed everywhere. But there is some difference. You cannot really put your finger on it, but you can tell there is some difference in the shape of this measurement outcome distribution. This is in the early state. But as you go into the late state, any distinction between these two different initial states are kind of washed out. So in learning the learnability transition, the mission is to be able to tell that this pile of data is different from this pile of data. And you only will be able to tell that in the strong monitoring limit. But even then, you only have a small, narrow window of opportunity at early times. So knowing what is the kind of challenge that we have, what kind of structure the data has, and where my opportunity lies is the key information in designing how we approach this from machine learning perspective. Because meaningful information really occur in the early times, we want to learn the evolution of time. So that's going to be done through temporal attention. But what is changing is the distribution, shape of the distribution. So we need to learn distributional property. We're going to do that through inter-trajectory attention. And the way we designed our machine learning model is such that we can start taking things out and see when what breaks, and therefore know what is it that our model is learning. When you think about learning, for me, it becomes very, I become very invested and very personal when I think about my kids learning. I want them to learn. I know what they want to learn, but I also want them to learn the right thing for the right reason. And it's the same same criteria that I approach when we look at the machine learning outcome. We would like models to learn the right thing and learn it for the right reason. Only then we can trust what it predicts. So here is the result. We found that with the modeling the experimental level of noise, so this green is the noisy data, and we can still learn this measurement in this phase transition. And most importantly, we can learn with, pretty reasonable level of sample complexity. How much time do I have? 3 minutes, okay. So let's see, I guess I don't really have a lot of time left. So I just want to highlight that we've also taken this data-centric approach to develop decoder in the presence of logical circuit operations. And this work you can find here. Here, the data problem is that we have this syndrome measurement, and syndrome is affected by noise, and we want to consider how to do the decoding as we run the logical circuit. For instance, here we're considering transversal logical circuit, and transversal gates propagate noise when you do this two logical qubit entangling, and figuring out how to tackle that. It was the objective of this work. Long story short, given the limited time I have, what we came up with is this modular approach where we call it multi-core circuit decoder. We would train different decoder for different module for each of the finite gate set that we are using in our logical circuit. And then once we have this trained set of modules, we could parallel the logical circuit that we want to run with the decoder to decode the logical circuit in the presence of the data in the presence of logical circuit operations. And this logical circuit decoding approach actually has shown that it has comparable accuracy, but much faster wall time, because you really invest in the overhead of one-time training of your modules, and you can just unleash that. So I'm out of time. Let me just conclude. I talked about the kind of explorations and investigations that we've been taking on around the theme of quantum complexity and complex quantum states. There is the forward-looking, sort of upbeat, optimistic side of this, which is we might be able to solve some classically hard problems. There is a challenge that we have to overcome in order to work with the complex states and conquer them. That is, there is a challenge in readout. And I talked about one example of identifying a classically hard problem that is algorithmically defined that faces exponential blow up, and finding an alternative quantum strategy for it. And the strategy of using AI algorithms that are tailored for the particular data structure and the learning mission to address the learning challenge of the readout. With that, thank you for your attention.
Minutes for questions. There are 2 mics on the side here if people can kind of mosey up to those to ask so everyone can hear.
I want to be complimented for model behavior. Ending
exactly on time, yeah. Yes.
Right?
We're off to a great start. Yeah. Oh, is it not on?
I'll just say it very loudly for us to get it. Well, I don't know, like, there's these circuits that people have for string nets. So did you sort of explore them? Are they just 2D, or is it the compilation of the unitary?
So there were other generally there is no way out of linear in depth of just because it's a topological state, but I don't know. Before us, I don't think it was like our approach really. The strength was we had a sort of a systematic way of growing this from the smallest to make it larger and larger. Our understanding, based on what's available in the literature from other papers and estimating the cost, the prefactor of our strategy seems smaller than what was available before. But this was the first case where stringnet condensate was prepared and sampled. Now there was a competing paper from Tsinghua Group where they also prepared Fibonacci stringnet condensate, but their focus was more generating the anyons and braiding. But I can go into like hours about why ours is better, but I'm not going to do that right now.
Thanks.
Ours is 2D. Short answer.
Yes, thanks for the nice talk. I guess maybe a follow-up question to that. And I think you've sort of touched on it, but just want to make sure I understand correctly. Like, how do I think about the effect of noise? Like, maybe specifically in the first part, but I also kind of wonder about other parts as well. Like, is there a statement that the algorithm will be robust against hardware noise? Or like, and also, I guess I want to put that into context. Like, is the claim that you're doing that with fault-tolerant error correction, or without error correction, or with non-fault-tolerant error correction? And how do I think about that result in the context of, naively, I would think if you have like a finite rate error, then there like at some point like the circuit will be efficiently simulable classically.
So this is right. This didn't even need. Actually, we needed to run a Mathematica code to, by the time you have 4 plaquettes, it's already something that you want to do it algorithmically, so it was done on a classical computer, but we did it in classical computer, so clearly this is not anywhere in the regime of quantum advantage. How do we think about robustness? So here, the red line is a countout from the experimental data. None of these states should have been there. They violate a rule. It's called branching rule. They violate the branching rule that defines Fibonacci stringnet condensate. So anything that we see here are effect of noise. Nevertheless, I'm proud of this because if you look here, these are the allowed states. And clearly, the allowed states have much higher amplitude than non-allowed states. So this is this is like seeing so-called topological protection, in front of your eyes. The fact that these are suppressed is giving you sort of how this whole topological robustness works. But they're not zero. So to actually make them zero, you need to do error correction on top of this, which we haven't done yet. But, so this is with just physical qubits. There was no error correction done here. But I still think of this Fibonacci string net sampling as an interesting, tantalizing challenge for the day. I don't know who are doing hardware, Pedram, 5 years from now, 3 years from now, for the day when we have like fault-tolerant 100 qubits. when we have fault-tolerant 100 qubits, what?
5 years from tomorrow.
From tomorrow, okay. Or from 5 years from your talk. So I want us to be thinking about, I personally would like to think about what kind of things that do we want to do, with the fault-tolerant qubits. So why this particular? Because the sampling complexity here is, at least, it's still going to be exponential, but the prefactor is clearly smaller because it's a smaller space. So I think, again, there possibly is a window of opportunity where something hard otherwise can be done, and it is a problem that has a history, something that existed. I would claim it goes right back to Ada Lovelace, and I like her. Yeah.
Yeah, thanks a lot.
Maren, do you have a question?
Thanks. So I have a question about the second part of your talk, the learnability transition. So transitions are something that happen in the thermodynamic limit. What system sizes did you reach, and how does the algorithm scale as you increase the system size?
Tough guy. Okay, so let's see, so here, I'm a humble and practical person, and I had a very humble goal here. My humble goal was, I would like to see this fascinating notion of dynamical transition in action in an experimental system without, in the regime where you cannot do classical simulation. Whether it is a phase transition in some particular sense, whether I can assign criticality, that's a next level question. That wasn't my battle. Okay. But this, like 20 is where we stop, because that's how far we can go with classical computer. I mean, if you throw resources and be clever, you can probably go a little bit higher. But what I find promising is that, the sample complexity here is like, I'm asking for 700 bit strings. That's got to be doable, right?
Hi, thanks for the nice talk. I have 2 questions. The first one, at the end, you talk about this modular decoder. Is there
I talked about what?
The modular, I think you call it.
Oh, yes, modular decoder, yes, MCCD. Multi-core circuit decoder. I remember.
Oh, sorry, multi-core.
Yeah. Anyway, it's modular, that's right. Modular is an important word that I want you to remember, yes.
May I ask you, so do you see any obvious problem if you extend this from stabilizer codes to something that's not a stabilizer, in particular non-abelian codes?
No.
And
there isn't any problem with the strategy. I think the strategy is very versatile, and it should be applicable for codes that are non-stabilizer code. The thing about trying to do something with machine learning, I try to emphasize how knowing the structure of your data and the traits of your data is really important. We cannot really do something meaningful and make meaningful claims without having data at hand. I think in principle, I don't see any aspect of our approach that limits us to the stabilizer code. But stabilizer code data was what we had in hand, and that's what we've experimented with. But I would love to, collaborate with someone. If you have different type of code and data, I think it'll be really interesting to try to do this in other types of codes.
Thank you. And the second question, when you prepare these string nets, in particular for Fibonacci, so nowadays, so people may prepare some easier quantum double systems. Is there any particular problem? Say you have a bunch of problems in coloring graphs. Do you think is there any advantage on preparing those simpler or finite depth circuits?
Right.
To do
So,
coloring
so
or decision problems?
thank you. So it was not just about preparing a state. You know, preparing a state is nice and fun, and you know, it's an act of creativity. We like to create, but I'm being more utilitarian. I want to create a state that have some, you know, muscle, something that it can do, some win, some trophy that it can put under its belt. And this Fibonacci string net condensate has that trophy associated with it, which is something that we found really interesting. But I don't have anything against other creative states.
But is it for decision and coloring problems, or as a state of matter to do fault tolerance? What is the?
Not for fault tolerance, but for this solving classically hard problem as an example of a problem where you are doing something that's classically hard from a sampling perspective. I mean, that's $1 million question, right? Where can you generate value? In my mind, that's a very important question, and it is a direction. That general direction is a direction, but usually very hard because of the sample complexity that grows. So we got really excited about this because we were seeing that it presents a window of opportunity.
Thank you.
I had a slightly related question, which was the choice of that problem in any way related to the connectivity of the underlying hardware?
No, it wasn't related to the connectivity of underlying hardware. Choice of that problem really goes back to my earlier work with colleagues at Google, where we did this Ising anion braiding. And the reason why we were able to do this Ising anion braiding was because the way we implemented this idea of bulk Ising anion was moving outside of the rigid thinking of perfect lattice. So anyways, encoding is done through the corner, but we brought the corners in, and that was Yuri's idea. Let's think about graph, because you're thinking about connectivity. Mm-hmm. There is no reason why you have to obsess over translational symmetry. Anyways, these are artificial states. What we wanted to do with the Fibonacci was to continue to develop that idea that when we think about local connectivity and graphs and use that as an angle to build out an interesting state, that can be a very approachable strategy for near-term hardware. Mm-hmm. So we approached the Fibonacci string net from that angle because it is a different type of anion than Ising anion, which it can actually do universal quantum computing. And if you braid, you do non-Clifford gate. So there's sort of intellectual interest. But as we explore this, we realize there is another opportunity outside of let's do universal gate with braiding. And that we did that too, and that's also fun, but I kind of got really excited about this alternate utility of this state. But the beginning it was not the heavy hex geometry, it's that we were thinking about the local connectivity. Yeah.
So maybe one more question while the next speaker gets set up.
Yeah, thank you for this talk. Would you mind go to the slide you're showing the result for this measurement-induced phase transitions? Maybe one slide.
Okay, I think I know how to.
So you have a plot showing the noise, the transition with noise.
Yes.
Yes. I just wonder for this, it's like the noise model is you get it from.
We use continuum noise model for this. Yeah.
I see. So it's a specific noise model.
Yeah, because I was taught by Roman that this kind of preparation is actually very well suited for trapped ions. So we were thinking about trapped ion hardware, and to model noise, you need some sort of grounded guidance, and we were using the noise model associated with the continuum hardware.
Yeah, because I'm curious about how all these AI-based approaches, how robust, what's the pre-knowledge we need about the underlying noise, and I also assume if your noise is too big, it may fail at some point. I'm just wondering, is there a...
So I would love to work with the experimental data, then I don't need to model noise. Experimental data come with the noise model, and I don't need to teach my machine learning algorithm what the model is, because I'm not trying to simulate and compare. I don't do forward modeling and trying to compare. We just try to learn what the data looks like. So that's what we would really like to do. But we wanted to do this benchmarking to give some confidence to our experimentalist colleagues that, look, this can be done. And I'm not going to ask for, hundreds of thousands of bit strings. I'm only going to ask for thousands of bit strings. So that's why we went through this exercise.
So if you add significantly larger noise, will the whole thing kind of fail?
If the noise is significantly larger, it might be harder.
I see.
But I'll have to try.
Okay, thank you.